All right. Good morning, everyone. How's everyone doing? Have a good weekend? Good weekend. Awesome. And nice. Not a snow day yesterday. I guess it was a cold day, but that was kind of nice. So today we're going to continue on. We're actually taking a little bit of a detour today from what we've been talking about to talk some more about GIS. I know many of you are probably familiar with the concept of GIS, but maybe don't know a whole lot about it or haven't used it. So today I'm going to be giving a brief introduction of GIS technology, and we're going to begin talking about the ways in which it's used in landscape ecology so that as we talk about some of the more detailed aspects of landscape ecology and we begin to use the actual GIS technology, you'll be better versed in what it's all about. So let me share my screen here. One sec. All right, so today's really going to be an introduction to GIS. Again, for those of you who don't know too much about it, we'll be talking about what it is and some of the ways in which it's used. So we'll begin with the question, what is GIS? And the whoops, sorry, this is going slow. Definition of GIS is that a geographic information system, or GIS, integrates hardware, software, and data for capturing, managing, analyzing, and displaying all forms of geographically referenced information, right? So in other words, what that means is that it's a system that allows for the georeferencing, or in other words, mapping of data, which makes for a powerful analytical tool across a wide spectrum of applications, right? So any type of data that you can collect is going to have a geographic component to it, since everything that happens is happening in a place. And when you connect the location of that data to the data itself, then you can begin to reveal patterns and relationships that you wouldn't otherwise be aware of. So any GIS system consists of three basic components that work together in concert. The first is the technology. So that's the software that's used, as well as the technology that we talked about earlier in the semester that collects all of that data for remote sensing, for example, through satellites and aerial photos and things of that nature. Boy, this thing's slow. And then next is the actual data. So there are different types of data that we'll be talking about that's used in GIS, and we'll be talking about the ways in which those different types of data come together to give GIS its power. And then, of course, the people who are involved in creating the maps, collecting the data, digitizing that data, and then making the decisions about how that data is going to be used in terms of planning applications or design applications. And these are, of course, some of these are like really old photos from back in the day of GIS. But it's, it's something where it's a tool that's useful for decision making and is not necessarily leading to an answer, so to speak, to any given problem in and of itself. Nearly every industry that you can think of makes use of GIS technology. So these include banking, insurance, defense, intelligence, education, economic development, public works, public health, cartography, agriculture, come on, conservation, forestry, mining. Don't know why, something about Zoom likes to slow down everything on my computer. Mining, public safety, transportation, all sorts, ethnography, all sorts of different types of fields. And in fact, you might be thinking like, oh, landscape architecture isn't in here. And yes, it is also used in landscape architecture. But the kind of interesting thing about it is that until recent years, it hasn't been used all that much in landscape architecture. And we'll talk about that in a moment. But to give you an example of the way that some of these fields use GIS technology in banking, it's used for tracking home values, fraud monitoring, looking at patterns of foreclosures. In K through 12 education, it's used for facilities management, vehicle routing, district boundary mapping. So for example, you can take information about the population of kids within a certain age range, and you can break that up over a map to determine which kids should be going to which schools so that they're evenly distributed. And you can use GIS to help determine what the appropriate boundaries are for different schools. In public works, it's used for transportation and water infrastructure monitoring, urban forestry, and expansion planning. So thinking about how some of the different utilities that we use need to be expanded, how they're servicing the existing population. In public health, it's used for illness outbreak monitoring, demographic information targeting, and other purposes. It's actually been used very widely in the current public health crisis with COVID. From a very early time, they've been using maps to monitor outbreaks of COVID and hotspots, and using that to figure out how it's spreading and how best to contain the spread, although obviously containing the spread has been feeble at best. In agriculture, it's used in the identification of optimal farmland, monitoring of crop yields, maps of organic operations, and other purposes. Transportation, it's used for traffic monitoring, infrastructure mapping, transportation planning. So thinking about how transportation is servicing the population, what places it can access, what places maybe are transportation dead zones where there isn't good access to transportation, so that future improvements can be targeted to the places that need it most. In ethnography, it's been used for mapping ancient trade routes and natural resources and tracking linguistic patterns. So looking at how goods and knowledge and culture has moved over the centuries across different cultures. And then the output of a GIS system can take many forms, and those can be both as hard copy or digital. That includes printed maps and diagrams, map series, so you can actually automate the creation of a series of maps based on showing either different types of data or over various geographic expanses. They can be used as static web displays or more often as interactive maps. I showed you guys, I believe I showed you guys an example of the research work that I'm doing with renewable energy. Did I show you guys that at the beginning of the semester? The Bright Fields project?
Yeah, I remember that.
Okay, so that's an example of an interactive map, right? Where you can search for things, you can filter out the types of results that you're getting, you can turn different layers on and off, so you can interact with that map to customize it to show exactly the type of information that you need. You can also output GIS as vector files for AutoCAD. And for that reason, it's actually one of the best places to go for base information when you're starting on a new project. It's typically one of the first places I go if I'm working on a new project and I don't have a good survey to work from, for example, which is often the case. GIS is often the best place to start because you can get building footprints and property lines and utility lines and bodies of water and streets and all sorts of information about that piece of property before you're able to get a survey completed. So you can take all of that GIS data that's already freely available and convert it into AutoCAD so that you can create an AutoCAD base file. And then it can also be exported. You can do 3D exports for modeling applications. So the latest versions, ArcGIS Pro in particular, has 3D capabilities so that you can visualize, for example, buildings in 3 dimensions. And that information can be exported to modeling applications like Rhino and SketchUp and other software like that, so that you can use that again as background information for models that you might be creating for a project. And then also spreadsheet ready data tables, right? So it's not just about the geographic and the information about the shapes that are on that map, but it's also about the data that's underlying those geographic objects. And so all of that data can be exported as an Excel file or some other spreadsheet ready data table. The software that we use in GIS takes many forms, both as online browsers and as local server-based applications. So this is one that you guys are all familiar with at this point. This is Google Maps, which can be thought of as a sort of basic form of GIS in which it shows different types of information, right? You go beyond just simply seeing where the roads are, where the buildings are, but you can begin to do searches for types of businesses or for specific places, for things like transit stops and so on, so that there's a lot more information that's baked into that map beyond simply the locations of things. And likewise, many municipalities have their own GIS systems. So this is an example from the city of Miami, but there's also the city of Fort Collins has its own mapping portal. City of Denver has a mapping portal. And these mapping portals are, again, they're not simply just street maps of that location, but they are ways of visualizing all of the available GIS data for that municipality. So if you go to FC Maps, which is the name of the mapping portal for the city of Fort Collins, they have a bunch of different layers that you can turn on and off, and I'll show an example of this a little bit later. But they have different layers of GIS data that's available for download that you can turn on or off in their mapper. So you can visualize that data before you go through the trouble of downloading it and bringing it into your own GIS application. And then, of course, we have the actual GIS desktop software that we use. This example here is from ArcGIS Desktop. Now what we use is ArcGIS Pro, which looks pretty similar to this, but definitely a lot more contemporary in terms of its layout and the way that you access tools and so forth. And we'll be working in ArcGIS Pro for the remainder of the semester. I hope everyone was able to download the software and get it installed by now. You should have all received an email from Esri that has your login information for ArcGIS Online. So that's your username and your password for ArcGIS Online. That lets you log into ArcGIS Pro, but also log into ArcGIS Online, which we'll also be using this semester. So hopefully you guys all have that. If you have had any trouble getting that installed, please let me know and I can try to help you get that installed so that you're ready to hit the ground running once we're using the software in the next few days. So next we'll look at a brief history of GIS and how it developed over time, and how maps first came to be used as analytical tools. So the history of GIS, of course, is embedded in the history of mapping itself. And if you think about it, even the earliest maps are kind of a primitive form of GIS, which places people and events in a geographic context. So this is a map of Bristol, England, which at that time was known as Brightstow, from the year 1574. And you can think of this as a form of GIS, which is showing various information about this town. So what's some of the information that we can get from this map?
They have a primary water source.
Yep, so you can see the water bodies on there, specifically the river that's running through the city. What else?
You get a
Road-
list of, like,
like streets, residential, and then like farmland.
Yeah, so it's actually showing different types of land uses, right? Which is not something that you typically think of seeing on a basic street map. But we're getting an idea of like where people live, where the farmland is. What else?
circulation paths.
Yep, circulation patterns in terms of the road layout. Anything else?
Location of the wall and other defenses.
Yep. So you can see some of the old city defenses here, some of the walls up there, and then there's one down here. Then there's one other piece of information I'm looking for.
The agricultural patterns.
Yep, we have where the farmland and the agricultural patterns are that I think somebody else mentioned that as well. If you look at the buildings in the town, what information can you get from that? So one of the things, well, there's actually two pieces of information. One is that they've illustrated different types of buildings differently so that you can get a sense of where the important civic buildings are or places of religious importance. But also just by mapping out where the homes are, you also get a sense of population density, right? So you can see where there's higher population density, where the population is more sparse. And so there's really a lot of information that's kind of embedded in this map. And if we fast forward to the 1800s, one of the first instances of a mapped data overlay that was used for spatial analysis was during the 1854 London cholera outbreak with this guy, Dr. John Snow. Sorry, that's the wrong. This guy, Dr. John Snow, wrong John Snow. And at that time when cholera was spreading, the prevailing theory was known as miasma theory, which is the theory that inhaling foul vapors caused the disease. But this guy, Dr. Snow, was a skeptic of that theory. And he set out to prove that the disease was spread through other means. And so what he did is that he went around and he mapped the locations of cholera deaths, as well as the locations of the public water pumps to try to see if there was a pattern that could be revealed. So in this map, you see these little black bars here. Each bar represents one fatality from cholera. And so he went around to different addresses and knocked on the doors and asked, like, has anyone here died from cholera? And he made a map of all the deaths in different locations. And he also mapped out the locations of the water pumps in the city, which was where people would get their public water supply. And so you can see there's a pump here, there's a pump here, there's another pump down here. And so through interviews with some of the families of the victims, he found out that obviously many of the deaths were clustered right around this, what's known as the Broad Street pump right here. And he also found out that many of the people who had died who did not live close to the Broad Street pump worked or went to school adjacent to the Broad Street pump. So we're still getting at least part of their day's water supply from that pump. And he reported these findings to the city health officials, and they really didn't find this all that compelling, unfortunately. And they said, you know nothing, Jon Snow. And so he was left to his own devices to try to see if he could fix the problem himself. And so he actually got a couple of friends together, and they went out and they unbolted the pump from the street for the Broad Street pump and removed it so that nobody could use it anymore. And within a matter of about a week, the cholera was magically cleared up and nobody was getting sick anymore. And so that helped to convince people that it was actually a waterborne disease. And it turned out that it was later discovered that fecal matter from a nearby cesspool was leaking into that well. And so people were kind of drinking raw sewage, which turns out to be not so good for your health. And so that was really one of the first examples of using data and specifically maps and patterns in order to solve a problem, in this case, a public health problem. Now we'll fast forward to the mid-20th century, mid-1900s. So, and we have this guy, Ian McHarg. How many of you know who Ian McHarg is? You should all know his name. Yes? Can someone tell me who Ian McHarg is? Anybody?
Didn't he create GIS?
He did. He's known as the father of GIS. We'll talk about why in a moment, but there's more to that. What else is he known for? You guys cannot be third and fourth year landscape architecture students without knowing who this is. No one?
Landscape architect.
Yes, he's a
Guessing.
landscape architect. He was a landscape architect. He was actually Scottish, but he moved to the United States in his 20s. And he was the head of the landscape architecture program at University of Pennsylvania. He was a graduate of the of Harvard's landscape architecture and urban design programs. And most importantly is that he had a deep belief in the power of natural systems, and that that human designs on the landscape should be working in concert with natural systems, which sounds like an obvious thing these days, but at the time in the mid-20th century, that was kind of a radical idea, because that was a time when science and technology and design were all about controlling nature and subverting it to human purposes. And so he was one of the lone voices who was saying, wait a second, there's a lot to be gained from natural systems and understanding them and designing with them. And he wrote a book, here it is, Design with Nature, that was a treatise that outlined his philosophy of design and his philosophy of designing with natural systems. It's considered a classic of the landscape architectural canon, and still to this day is one of the most widely read design texts in landscape architectural history. So this book, it was like one of the really big sort of important texts in the history of landscape architecture, Design with Nature. And so of particular interest with regards to the development of GIS was a process that McHarg outlined in the book that he had been developing over the previous decade, in which various types of assets, or what he called assets, both cultural and environmental assets, could be mapped in the successive layers to assist with site selection for various development and design uses. And these are some examples of diagrams from the book that show this process. And by mapping out these assets and overlaying them, he could not only, in that way, he could not only see like kind of the areas of the highest value, but also determine how best to propose various landscape or design or urban design types of projects so that they would do the least damage, for example, to the various assets available. So this is an example where McHarg's analysis was looking at a portion of Staten Island where a controversial highway project was proposed. And various groups involved couldn't agree on what the most appropriate route for this roadway would be. And so McHarg was called in to use this process to look at the different types of values. And so here he looked at historic values. And in this case, what we're seeing is that darker areas are higher value and lighter areas are lesser value. And so he mapped out historic values, scenic values, again, darker tones being greater value, recreation values, residential values, institutional values, wildlife, forest values, water values. And so he went through and mapped out all of these, and this was done essentially on sheets of acetate that could then be overlaid on each other so that you could see through and build up these layers of values that combine all of those different asset types. So that places where you had the darkest shades would be the places that had the greatest value. Right, so this is what you get when you superimpose all those layers. And it shows, you know, the areas that are kind of the blackest colors are where you have the highest values of those different assets that are all overlaid on top of each other. And then the areas where you have the lightest color, like the whites or the light grays, are the sort of paths of least resistance, where you're doing the least amount of damage to those existing systems. And so he was able to use that to propose a route for that roadway that tended to avoid the most sensitive areas. And so that formed the basis of his recommendation for the proposed highway route. In the end, that highway was never actually built, but this process proved to be an extremely valuable way of analyzing geography and analyzing the different types of systems that exist in geographic areas and using it as an analytical tool. And because of this framework that he developed, he's considered to be the father of GIS. And this is still, to a large extent, the basic framework that's used today in computerized GIS systems. McHarg was also he was the first to demonstrate that many types of social factors could be analyzed and mapped as well. And so he looked at mapping all sorts of things. So things like homicides and suicides and levels of drug addiction and alcoholism and robbery, rape, aggravated assault, juvenile delinquency, infant mortality, and all sorts of other social factors like that to, again, show that you can use this analytical process to target resources where they're most needed. And then with increasing accuracy in mapping and data collection technology, we've had increasing utility in GIS applications, right? So we have aerial photography that started to be used in the early 20th century, and throughout the 20th century. And of course, that starting in really the 1950s and 60s, that was supplemented by satellites, which would collect information remotely about the Earth, so that it was almost as if you're sending out, thousands of surveyors all at the same time to survey the land. You could collect massive amounts of information that way. And then, of course, there have likewise been improvements in computer technology, which allows information from data tables and maps to be digitized and georeferenced, which also greatly enhances GIS functionality and applications. So not only did we have this explosion in the ability to collect data, but at the same time, we're having an explosion in the ability to analyze and map that data. And so this is really when GIS began to take off as a powerful analytical tool. So the first true GIS system worldwide was developed by this guy, Dr. Roger Tomlinson, in Ottawa, Canada, back in the 1960s. And his agency produced a short film called Data for Decision, which is a classic depiction of early GIS technology. You can look it up on YouTube. It's still available on YouTube. It's kind of hysterical to watch because of the little sound effects and bleeps and blops of how they represented computers back then. But the basic process for GIS analysis is exactly the same today as it was back then, except instead of using punch cards and these very sort of cumbersome computing technologies, we have all of that built into our software that we use directly on our desktop now. And then in the late 1970s, the Map Overlay and Statistical System, also known as MOS, was the first widely used US government GIS system, and that was actually developed by the Western Energy and Land Use Team of the US Fish and Wildlife Service right here in Fort Collins. So the very first US widely used system of GIS was developed here in Fort Collins. This is from a report that they created on that system. And in fact, that helped spur a whole GIS industry in Colorado, along the Front Range in particular. And some of the biggest players to this day in GIS technology are located along the Front Range in Colorado. And there's a stretch that goes from Fort Collins down to about Pueblo that's known as GIS Alley. And some of the biggest names in GIS technology and data collection are still to this day located along that corridor. In 1969, Jack Dangerman was another graduate of Harvard's Landscape Architecture program, and he was a researcher at the school's Laboratory for Computer Graphics and Spatial Analysis. And he was very interested in the use of maps in analysis, and he founded a company called Environmental Systems Research Institute, also known as ESRI for short. And Esri is you guys should all recognize that name by now. That's the company that produces ArcGIS. So in 1982, they released the first version of ArcGIS, which is now the industry standard for GIS software. And in fact, Jack is one of the Forbes 400 wealthiest people in the world, based on that software and how widely it's used in all these different industries now worldwide. Jack is still very much involved in the company and in GIS technology. He hosts the Geo Design Summit that I go to I go to most years in February. Of course, this year it was virtual. but he still hosts that as well as all sorts of different GIS conferences around the country. And so this is a photo from the 1960s from the Harvard Laboratory for Computer Graphics and Spatial Analysis. And Jack Dangermond is second from right in this photo. He was the founder of Esri. And then also in this photo is one of his colleagues, Carl Steinitz, who is actually the guy that I learned GIS from when I was in grad school. And he is also somebody who's been kind of very important in the development of GIS technology. He was the one who came up with the term geodesign and sort of outlined a framework for using GIS as a tool for basically informed decision-making in design. All right, so that is the overview of GIS. And now I'm going to jump into, let's close this. We'll begin talking about GIS data. I don't know if we'll get through this entire presentation today, but if not, we'll just continue it on Thursday. Sorry, that file is opening. So any questions about sort of the genesis and history and uses of GIS before the while this next presentation is opening? It's kind of ironic that it was created by a landscape architect and then not used all that much, and it exploded in all sorts of other industries, and it's really been only in the last 10 years or so that landscape architecture firms have started making wide use of it as well. All right. Okay, so second portion of this lecture is talking about GIS data and the types of data and some of the ways that we can find and use that data. So in order to begin, first we need to talk about GIS data types in the context of computer graphics in general. And specifically, we're going to be looking at the two major types of computer graphics. What is going on here? Sorry, I have all kinds of weird windows opening up. Okay, so first we're going to talk about raster graphics. And a raster graphic is defined as a rectangular array of discretely colored pixels or dots that are displayed at a given resolution or density. The data structure saves the information on the exact color of every pixel for an entire image. And then the other type of computer graphic we have are known as vector graphics. And a vector graphic is a mathematically defined series of points connected by straight or curved lines extending in 2 or 3 dimensions. And the data structure is a set of instructions that tells the computer how to recreate the image, such as draw a line from point A to point B, and then a curved line from point B to point C, and so on. So they're kind of two very different ways of creating graphics in a computing format. So some examples of raster graphics include digital photos. So when you take a digital photo with your phone, for example, it's collecting light information and converting that into colored pixels on the sensor. And so it's just a grid of colored pixels, which is a raster graphic. A scanned image basically is the same idea, but using a scanner bed. Photoshop is also a raster graphic tool. So any kind of renderings that you might create in Photoshop are also raster based. And then for vector graphics, we have AutoCAD drawings. AutoCAD is the main vector tool that we use in creating graphics in landscape architecture and in design in general. Rhino or SketchUp models or any sort of 3D software is also using vector graphics. And Illustrator is also primarily a vector graphic tool, although it actually has some really good raster tools built in as well, so that you can kind of blend the two types of graphics using Illustrator. All right, so to give an illustration of raster graphics, so here's a blank screen. And these are pixels, right? So when we talk about pixels, they're just little squares of color on your screen, and it just divides the screen up into a grid, essentially, right? So if we take a raster image of this place, which is one of my favorite North American cities, which is, what city is this?
Is that Boston?
Nope. Anyone else recognize it? So
Chicago.
Yes, it's Chicago. So this is the Chicago River. One of the buildings that gives it away is this building right here, which people refer to as the Corn Cob Building. It's actually it's a parking garage and a series of condos above that. But that's kind of one of the iconic buildings that you can recognize from Chicago. But anyway, if you haven't been to Chicago, I highly recommend that you visit there. It's an awesome city. So here's a photo of Chicago. If we overlay a grid on top of that to break it down to pixels, and then let's take a section of that and enlarge it. So here's a 400% enlargement on a portion of that photo, and then we'll zoom in again. 1600% enlargement. And then finally a 6400% enlargement. And you'll quickly realize that this is no longer recognizable as Chicago, or really as anything at all except for a bunch of colored squares. And again, that's because of the way in which that data is stored for a raster graphic. So in this case, it's stored in RGB values. So those stand for red, green, and blue. And each of these has a value that ranges from 0 up to 255 for a total of 256 values for each color. And that gives us about 16.5 million different colors that you can represent through this combination of red, green, and blue values. And so that's essentially how the data structure is stored. Some of you may be familiar with the fact that there's not just RGB color space, but there's another major one that's also used. Does anyone know what that one's called?
CMYK.
CMYK, exactly. What does CMYK stand for?
Cyan, yellow, magenta, green. No.
Yep.
I don't know what K is.
Close. K is actually, it's a little bit counterintuitive, but it's black. And they don't use B again because B is already used for blue and RGB, but K is black. So it's cyan, magenta, yellow, and black. And CMYK. Does anybody know why there are these two color spaces, RGB versus CMYK?
Computer graphics versus printed graphics.
Yes, so it's screen graphics versus printed, because when you're looking at a screen, it's light that's being projected onto that screen, or it's LEDs. And what happens with light is that when you combine all of the different wavelengths of light together, what color light do you get?
White.
White, exactly. If you look at printing something, you're using pigments and ink, right? And if you combine together all of the different colors of pigments together, what color do you get?
Black.
Black, exactly. So RGB and CMYK are kind of the inverse of each other. And RGB is more appropriate to use when you're working strictly with screen graphics that are going to be shown on any kind of a digital device. And then CMYK is more appropriate to use when you're going to be printing out material because, again, those two color spaces are designed for either light or for pigment. All right, so now to contrast with the raster graphics, here's an example of a vector image. And this is a diagram from Illustrator. We'll take a portion of this here and we'll blow that up 400% and zoom in again, blow that up. Now 1600%, blow it up again, 6400%. And so what do you notice about this that is different from when we were blowing up the raster graphic?
It's not like pixelated.
It's not pixelated, exactly. It keeps its definition as form and the sharpness of the elements in it. And that's because a vector graphic is mathematically defined. And so therefore it's unaffected by changes in scale. So each of the things or objects that you see in a vector graphic is defined mathematically. So we have the formula for a line. There's a formula for a NURBS curve, which is a non-uniform rational B-spline, is what NURBS stands for. I hope you guys will all memorize that formula. It will be on your test. There's some corner coordinates for that polygon down the lower left. So you have all of these different sort of mathematical ways of defining these objects in the drawing. And what that means is that every time you zoom in or out on a vector graphic, the computer is using all these calculations to redraw that graphic entirely. And because of that, it's always redrawing it with nice sharp boundaries, and it doesn't get pixelated or distorted in the process. All right, so using that information about basic types of computer graphics, we're now going to look at how that applies to GIS data types.
Scott, I had one question about vector and raster.
Sure.
So why can a PDF be both vector and raster?
Yes.
All
So
Yeah.
that's actually one of the great things about PDF is that Adobe, so Adobe is, of course, the company that makes Photoshop and Illustrator and InDesign. And they figured out with Illustrator ways that you could combine together raster and vector graphics in the same document. And then a PDF is just kind of the natural extension of that, where it's like a, you know, kind of a static document that allows you to combine both raster and vector graphics into one document. And that's that's why PDFs have become the standard for, you know, all types of documents that you find on the internet now, because of that combination of different types of graphics. Because prior to that, you know, you could only have one type of graphic. So like a JPEG was a type of raster image, and you could only have raster data in there. Or a DXF was a type of vector graphic that could only contain vector information. And PDF was really the first file format that allowed you to have both in the same document. So yeah, so that's why PDFs are so popular and why they're used so much. So there are three basic classes of GIS data. The first is map data, and we'll talk about each of these in a little more detail. The second one is image data, and the third one is known as attribute data. And so the map data is the vector image format that's used in GIS. Image data is the raster image format, and then attribute data is data in a tabular form that is all of the kind of specific information about the features that are showing up on the map. And we'll talk about each of those in a little bit more detail. So first we'll take a look at the vector-based map data. This is the oldest type of GIS data architecture, and it was the type that was implemented by Roger Tomlinson at the Canadian Land Inventory. That was the very first sort of GIS system that was in use in Canada. And so map or vector data is expressed through a combination of 4 basic topological levels. So first you have the point, the line, the polygon, and then what are known as triangulated irregular networks or TINs. Right, so the most basic topological level is a point, which is just a discrete location in space. And so here's a point right here. And so in isolation, a point doesn't really have any significant meaning. It's the most basic topological unit, and it's static and finite. It's just a single point in space. If you have multiple points like we have here, so here we have 4 points together. Multiple points can imply relationships based on proximity and alignment. So in this case, you can imagine that those are defining the corners of a square, for example, by having those multiple points together. This is really the thinking behind the constellations, when ancient peoples looked up in the sky and basically connected the dots to create shapes. And then when you have large collections of points, particularly in 3D space, that's referred to as a point cloud. And that can imply both planar and volumetric relationships. So in this case, we have a collection of points in 3D space that begin to represent a human form. The next topological level is a line, which is a connection of 2 or more points, or a line can be thought of as a point in motion. Right, so a point can be straight or it can be curved, and it's inherently more dynamic as a type of representation than a single point, because it has the additional qualities of direction and length. And a line can also be referred to as a vector, which comes from the Latin meaning to carry or convey, which is why mosquitoes, for example, are referred to as disease vectors, because they carry or convey the virus particles that cause malaria, for example. The term vector is also used to describe a direction and a force in mathematics, which are the same inherent qualities in a line. A line can also be understood as the visual representation of a binary value in computing. It's the simplest form of meaningful abstraction, which represents an edge condition or a separation between 2 contrasting values or conditions. And then taken in disconnected groups, lines can convey patterns or forces, right? So the directionality of these lines, because they have a directionality to them, when you have many of them, they can create patterns that begin to imply, for example, maybe wind patterns or other types of forces. And again, they can be used to represent 3-dimensional surfaces as well, just like a point cloud. And next we have a polygon, which is a closed collection of lines. And a polygon can be thought of as the expression of a line in motion in a direction other than its axis, of course, and contains the additional properties of width and area. And a polygon defines an entirely closed area, and as such is a static object, right? So here we have a hexagon. Although if you begin to combine polygons, it implies different types of relationships, of course, right? So a single polygon in isolation is typically understood to be a continuous uniform surface. But when you have one that's enclosed by another, what does that begin to imply? So in this, where we have the hexagon enclosed by a rectangle, what is that? It can imply a couple of different things, but what's one of the things that it might imply? A hole, yep. So it can imply that there's a hexagonal hole in this rectangular surface. What else can it imply?
A difference between the two?
Yeah, a difference in maybe materiality or surface condition between the two. So if you're thinking about this in terms of a site plan, maybe this area out here is brick and this area is stone, right? So those edges, again, are defining that there's a difference in something about those two conditions. And then, of course, large collections of various polygons, which can either be distinct or overlapping, form the basis of most complex representational line drawings, like in this AutoCAD site plan. And then finally, the highest topological level, at least in GIS, is the triangulated irregular network, or TIN, which is a three-dimensional surface that's defined by a series of interconnected polygons, typically triangles, which is why it's called a triangulated irregular network. When you see it from above, it simply looks like a series of flat connected triangular polygons. But when you see it from an angle, it implies three-dimensionality. And it quickly becomes apparent that it's used for surfaces, most often for topographic surfaces, so showing terrain, for example. And then ArcGIS, a TIN is typically generated in one of two ways, either from a point cloud, which is typically the result from LiDAR data. So LiDAR data is collected as point clouds, which can then be converted into a terrain model as a TIN, or it can be converted directly from contours, which can be either lines or polygons. And then it can interpret those polygons if they're given height elevations for each one of those contours to determine the terrain model. So all of those different topological levels of map data are used to represent different types of geographic features. So points are specific discrete locations described as X and Y coordinates. These can be things like a street address, a tree, or a utility pole. Oftentimes these are represented using symbols rather than simple dots. Then you have lines, which are any feature whose width is negligible in comparison to the length. These include things like streets, rivers, and railroads. So basically anything that's long and skinny, essentially. Polygons are used to represent any feature that has an enclosed area or boundary, such as a building, a congressional district, or a state boundary. And then TINs are typically used for topographical features and terrain. So to show an example of this in a sample GIS map. So here we have a sample, once it shows up here, there it is. Here's a sample GIS map of New York City. And here we find shapes, or in GIS parlance, they're known as features. So every discrete piece of information or geographic data is known as a feature. So a polygon is a feature, a point is a feature, a line is a feature. And so we find features on this map that consist of points, lines, and polygons. Right, so first, if we look at the points, in this case, they're using a little tree symbol, but those points represent the locations of parks. And then we have line features that are used to represent major roadways in this example. And then finally, polygons, which in this case are representing census tracts across New York City. Right, and each of those different topological levels provides the viewer with a different type of information in the map. And so you are constantly working with different types of topological features to represent different types of information. Whoops. Sorry, I don't know how that happened. Sorry, it fast forwarded to the end here. Give me a second to back up. Here we go. All right. Okay, so that's our New York City map. And then each of those different types of topologies used to represent different types of data. Now, since map data is vector in nature, technically it is scaleless. However, the accuracy of map data tends to vary with the scale that the data was drawn for. So even though vector data, you can zoom in on it infinitely, essentially, and it always looks like it's very accurate, it isn't necessarily accurate to every scale. It's accurate to the scale that was drawn for. So an example of that might be, here, an example of that might be, for example, if a state boundary was drawn for a map of the United States, if you zoom in really close to those state boundaries, you might find that they're off by a couple of miles and they're not exactly where that boundary should be because they were drawn at a national scale. And at a national scale, if you're off by a couple of miles, it's no big deal. But if you zoom in at a close level of magnification, then those couple of miles can become a very big deal. So it depends on who was drawing that information and what scale it was intended for. That helps determine the accuracy of that data. And because of that, the same feature can sometimes be represented using two different topologies. So one example would be cities on a map, right? So if you look at a map of the state of Colorado, how do they typically represent cities? What topological level would they use to represent a city? Would they use a point, a line, or a polygon?
Point.
A point, right? Because in the scale of the entire state of Colorado, a city is just a single dot, essentially. But once you zoom in on that city, so if you zoom in on Denver, for example, what topological level might they use at that point to represent the city?
Polygon.
A polygon, right? Because you're zoomed in enough that you can see the actual boundaries of the city and the shape of the outline of the city of Denver. So the same type of data can be represented using different topological levels depending on the scale that was intended for. So when we talk about map data in GIS, it's typically referred to as a shapefile and can be stored as a number of different formats. The first one is an SHP. I also list our SHX and DBF for reasons that will become clear a little bit later. But this is the native ArcGIS shapefile format. And it's actually not, even though it's referred to as a shapefile, it's a collection of a bunch of files, usually 5 or 6 different files that contain different types of information about the features in that shapefile. So when we refer to a shapefile, it's a small collection of individual files. And often when you find them online, they're all zipped together as a single zip file with all of those different file types contained together. There's also DWG or DXF, which are the native AutoCAD formats, which can be used directly in ArcGIS. DLG, which is short for digital line graphs, which is a format that's widely used or was widely used by the USGS in past years. You have MIF data, which is map info data transfer file. It's a format used by a competing GIS program known as map info, which is not used very widely anymore. SDTS, which is the Spatial Data Transfer Standard. That's the latest standard format that's used by USGS. They switched to that because it's kind of like a PDF in the sense that it can contain both raster and vector file formats. And then finally, there's VPF, which stands for Vector Product Format, which is the vector format used by the US Department of Defense for any kind of declassified military maps. But I have highlighted here in blue the SHP shapefile format because that's the one that we work with most commonly in GIS. Okay, and now we'll look at the raster-based image data in GIS, which offers many types of enhancements to GIS and many additional ways of doing analyses. And there are several different categories of image data or raster data in GIS. The first is thematic data, the second is continuous data, and the third is simply known as pictures. And we'll look at each of these in a little bit more detail. So first we have thematic data, which is also known as discrete or discontinuous data. And that's simply the raster version of map data, which represents features using definite edges or locations such as buildings and roads. Right, so this is an example of thematic image data. Typically vector map data is preferred because it's more accurate and you can do a lot more analysis using vector data. However, this type of data still exists because this is typically where that vector data comes from, is by scanning in a paper map that is then traced, or at least for historic data, that data is then traced and converted into vector data. And so a lot of times the only type of data you have to work with is this thematic data. And 99% of the time, the first thing you want to do is convert it into a vector format so that it can be more useful for analyses. The second and more common type of data that we use in GIS is known as continuous data. That's also known as field or surface data. And that typically represents values or features that don't have hard edges and that change more or less gradually over a given distance. So this is an example of what continuous data looks like. So you'll notice that there are kind of subtle changes in value, assuming that these different colors represent different numeric values, for example. There isn't like a hard boundary where blue changes to yellow, right? It kind of gradually goes through these different shades to go from blue to yellow. So what's one type of data that we might map that might be represented this way that doesn't have definite hard edges to it?
Population
Sorry, say that again.
population density.
Population density could be an example, although that's not typically the kind of data that I would associate with continuous data. Any other ideas?
Temperature?
What about
Temperature.
land cover?
Temperature, land cover, yeah, those are really good examples. So a lot of times it's associated with natural phenomena, like for example, wind speeds or temperatures, right? Where if I'm standing here and it's 73 degrees and I move over 2 inches, there isn't like a boundary that separates 73 degrees from 72 degrees. There's usually a gradation of, sort of an infinite gradation of temperatures in between. And so that's what continuous data represents, is those gradual changes in value. And this particular map actually shows, it's actually kind of a concerning map. Does anyone have any idea what this map might be showing?
Elevation?
Say that again.
I was thinking elevation.
Elevation's a good guess because, you over here near the Rocky Mountains, we have some different colors there, but that's not actually what it's showing. Any other guesses? It has to do with temperature. So these colors are actually showing the average temperature change over the past decade. And in this case, the reds and yellows represent the greatest increase in average temperature, and the blues represent the smallest increase. And so what you're seeing is that the highest increase in average temperature has been in the Rocky Mountains. And that's concerning for a number of reasons. What's one of the big reasons why that's so concerning in the Rockies? What's one of the problems that that's led to?
Wildfire.
Wildfire. And the wildfire actually is a result of something else.
Drought.
Drought, yep, that's also part of it. What else?
Just like climate change in general.
Climate change in general. And so for those of you familiar with the pine bark beetle, the pine bark beetle and the spread of pine bark beetle in the Rocky Mountains has a lot to do with the average temperature increase, because in the past, the pine bark beetle could not overwinter in temperatures that were too cold. However, with the average temperatures increasing, the pine bark beetles are moving to higher and higher elevations, and they're moving to colder and colder, or locations that in the past were colder, but now are just barely warm enough that the eggs of the beetles are able to overwinter and survive. And so that leads to larger outbreaks of the pine beetle, more deadwood in the forest, which leads to more intense wildfires. And then that leads to more intense flooding because you don't have the forest there anymore to hold back all of the soil and to mitigate the effects of heavy rainfall. And so that this has been a huge problem in our region because of that large increase in the average temperatures. And there's no happy thing at the end of that story. It's just bad news. So that's just kind of where we are with that. All right, so another common type of continuous data that's used in GIS is known as a digital elevation model, or DEM. And that's a common type of continuous data that's used by the USGS to represent topography. So this is an example of a DEM, and this shows higher elevations in lighter tones and lower elevations in darker tones. Right. And if you think about it, this type of representation is a much more accurate way of representing topography than a contour model or a contour map would be, right? Because contours imply that there's a line where it changes from 150 feet to 151 feet. But in most cases, unless you're dealing with terraces or things like that, it's a gradual change, particularly in natural systems, from one elevation to another. And so these continuous elevation types represent that a lot better. It is 10:45, that is the end of class time. So I will cut this off here and we'll continue with this on Thursday. And just a reminder, what's coming up 1 week from Thursday?
Yes,
Say that again.
The first exam.
The first exam, yes, is 1 week from Thursday. So everything that has been presented in lectures or in readings that have been assigned is fair game for that exam. So make sure that you're beginning to study that information and have it available. It is going to be an open book exam, but it's, you won't have enough time to kind of look up every piece of information. So the better that you can organize that information and study it, the better that you will do on the exam. So like I said, I'll cut this lecture off here. We will continue with this information on Thursday, and I will see you then. Have a good rest of your day.
Thanks, Scott.
Thank you, Scott.
Yeah.
Thanks, Scott.